Hi everyone, my name is Jaroslav Bendík. I'm from Masaryk University in Czech Republic, and I would like to present a joint work with my supervisor, Ivana Cerna. We focus on enumeration of so-called minimal unsatisfiable subsets. The input is a set of Boolean clauses, or equivalently a Boolean formula in CNF. So for example, assume that we are given these four clauses. You can see that the first two clauses contradict each other, therefore the formula is unsatisfiable. If you are given an unsatisfiable Boolean formula, you often want to somehow analyze the unsatisfiability. You want to identify the sources of the unsatisfiability. So how can we do that? Well, we can draw the buffer set. Then we can somehow determine which subsets are unsatisfiable and which are not, like this. And then we can see that there are two sources of the unsatisfiability, these two. The sources are called minimal unsatisfiable subsets. Formally, a set of clauses is a minimal unsatisfiable subset, shortly Mousse, if it is unsatisfiable and every of its proper subsets are satisfiable. Minimal unsatisfiable subsets found applications in many areas of computer science, such as formal equivalence checking, model checking, or Boolean model counting. The goal is usually either to identify a single minimal unsatisfiable subset or to identify or enumerate all the minimal unsatisfiable subsets. In this talk, we focus on the Mousse enumeration. Let me first describe a naive approach. Assuming that we are given a set of four Boolean clauses that constitute this power set. A naive approach would be to check individual subsets for satisfiability, like this, and once we check every subset for satisfiability, we can simply select the minimal unsatisfiable subsets. So let me now analyze this approach. There are several problems. First, it's practically intractable to check every subset for satisfiability, since there are exponentially many subsets. Second, the algorithm works in two phases. In the first phase, it checks every subset for satisfiability, and then in the second phase, it identifies the mousses. But the first phase is intractable. And third, in general, there can be up to exponentially many mousses, which means that the complete Mousse enumeration can be also practically intractable. In the past decade, there have been proposed several Mousse enumeration algorithms. These algorithms tend to minimize the number of performed satisfiability checks. They also enumerate mousses incrementally, one by one during the whole computation, which means that they are able to find at least some mousses, even in the intractable cases. And the rate of the enumeration is quite steady. In this talk, we present a novel Mousse enumeration algorithm called Unimousse. Like the contemporary approaches, Unimousse enumerates mousses incrementally, one by one, in a relatively steady rate. Compared to the existing solutions, Unimousse performs much fewer satisfiability checks, and consequently Unimousse enumerates mousses much faster. Let me start by describing several concepts and techniques that are commonly used by existing Mousse enumeration algorithms, including Unimousse. The first observation is about the monotonicity of the satisfiability function. Note that if you are given a satisfiable set of Boolean clauses, then every of its subsets are also satisfiable. Consequently, if we determine a subset of the input formula to be satisfiable, we can propagate the satisfiability through the power set like this. Similarly, if we determine a subset to be unsatisfiable, we can propagate its unsatisfiability like this. Another concept that we employ are so-called unexplored subsets. Naturally, a Mousse enumeration algorithm during its computation gradually explores satisfiability of individual subsets. Explored subsets are those whose satisfiability has been already determined by the algorithm, and unexplored are the other ones. To avoid repeatedly checking the subset for satisfiability, the algorithm has to somehow represent which subsets are still unexplored. A simple approach would be to explicitly store all the unexplored subsets, but there are exponentially many subsets, so this is intractable. Instead, we employ a symbolic representation that is commonly used by contemporary Mousse enumeration algorithm. Briefly, we introduce a Boolean formula called map, such that every model of map corresponds to an unexplored subset and vice versa. Therefore, to get an unexplored subset, we ask for a model of the formula map. Similarly, to check if a subset is unexplored, we check if it corresponds to a model of map. Yet another concept that we employ is so-called shrinking procedure. The input is an unsatisfiable set of Boolean clauses, and the output is a Mousse of the input. In other words, shrinking is a single Mousse extraction. There exist several efficient single Mousse extractor tools that we can use to implement shrinking. We are now ready to describe a Mousse enumeration scheme that we call Csharing Scheme. The scheme generalizes several existing Mousse enumeration algorithms, including Unimousse. The scheme works as follows. Initially, we mark all subsets as unexplored. Subsequently, we iteratively identify individual mousses. In each iteration, we first identify so-called seed. Seed is an unexplored subset that is unsatisfiable. In this particular example, we have 5 seeds, so we identify one of these seeds, say M. Subsequently, we shrink M into a mousse, say F. Now we can propagate the unsatisfiability of F to the power set, and by the definition of a mousse, we also know that all subsets of F are satisfiable, so we can propagate the satisfiability through the power set like this. And now we continue with the next iteration, so we find another seed. In this case, there is only one seed left, and that is N. So we shrink the seed into mousse, which is N itself, and then we can again propagate the satisfiability and the unsatisfiability like this. At this point, there is no more seed left, therefore it is guaranteed that all mousses have been identified. As I have already said, several of contemporary Mousse enumeration algorithms are based on this Csharing scheme. The difference between the algorithms is how exactly they identify the seeds, which seeds they identify, and also how exactly they implement the shrinking. Briefly, to identify a seed, all the algorithms repeatedly check unexplored subsets for satisfiability with a subsolver until they identify an unsatisfiable one, that is, a seed. The difference between the algorithms is which subsets they check for satisfiability. As for shrinking, the algorithms usually employ an external single mousse extraction tool, plus they employ some preprocessing techniques. In the case of Unimousse, we employ 2 novel techniques for finding seeds. One of them works on the same principle as existing techniques. That is, we repeatedly check unexplored subsets for satisfiability with a subsolver until we identify an unsatisfiable one. The novelty is in the choice of subsets that should be checked for satisfiability. The other technique for finding seeds works on a fundamentally different principle. We call it Mousse replication. Instead of checking subsets for satisfiability with a subsolver, we cheaply deduce that some subsets are unsatisfiable. Finally, to perform the shrinking, we employ an external single mousse extraction tool, so there is no novelty in this step. However, we propose some novel preprocessing techniques that are applied before the shrinking. So let me now show you how Unimousse identify seeds using a subsolver. Recall that we represent the unexplored subset with a Boolean formula called map, and to get an unexplored subset, we ask for a model of map. Let me call this subsolver a map solver. Assume that this black circle is the input set of clauses. To find a seed, we ask the map solver for an unexplored subset. So for example, let's say that we get this unexplored subset. Now we can check it for satisfiability, and we find out that it is satisfiable. So we just block this model of the formula map and we ask for another one, so this one, and we check it for satisfiability. Again, it's satisfiable. But eventually the map solver will give us an unexplored subset which is unsatisfiable. So we can use it as a seed and we can shrink it to a mousse. Clearly, we would like to minimize the number of satisfiability checks since they are quite expensive. Therefore, we should choose the unexplored subsets very carefully. The problem is that we do not know which unexplored subsets are unsatisfiable. Moreover, it is the map solver who gives us the unexplored subsets. The unexplored subsets are the models of the formula map, and we do not know in advance which model we will get. However, we can at least guide the map solver to give us some specific unexplored subsets. Some of the contemporary seed-shrink algorithms exploit a simple observation. Assume that you are given these 2 unexplored subsets. Know that the larger one is the superset of the small one. Consequently, if the small one is unsatisfiable, then the large one is also unsatisfiable. However, the opposite does not have to hold. Therefore, if you search for seeds among the large unexplored subsets, you can increase the likelihood of getting an unsatisfiable one. In particular, you can ask the map solver for maximal unexplored subsets, which corresponds to maximal models of the formula map. The problem is that the larger the seed is, the harder it is to shrink it. To find seeds that are relatively small and that can be found relatively quickly, we exploit, in Unimousse, the union of all mousses of the input formula. Assume that this blue circle is the union. Observe that every mousse has to be contained in the union. Consequently, it is enough to search for seeds inside the union. In practice, it is often the case that the union is relatively small, and thus the seeds can be indeed very small. The question is how to find the union. Well, unfortunately, computing the union is very expensive. Instead, we work with an under-approximation of the union. Let me illustrate it as this cyan circle denoted by U. Initially, at the start of Unimousse, we identify two mousses, and we set U to the union of the two mousses. Subsequently, we identify all mousses in U. To do that, we repeatedly ask map solver for maximal unexplored subset, and we are trying to find a seed. So we ask for maximal unexplored subset, we check it for satisfiability, it's satisfiable, so we ask for another one, and we find a seed, so we shrink it to a mousse. And we repeat this procedure. So we identify all mousses inside U. Once we explore every subset of U, we enlarge U. To do that, we find a seed inside the wall F. So we ask map solver for a maximal unexplored subset like this, we check it for satisfiability, it's satisfiable, so we ask for another one, we check it for satisfiability, it's unsatisfiable, so we shrink it to a mousse, and we use the mousse to enlarge the under approximation U. And now we find all mousses in the under approximation, and we repeat this process until we identify all mousses of the input formula F. Let me now describe the mousse replication technique, which is the second technique for finding seeds that Unimousse employs. In the previous slide, we have seen how Unimousse identifies seeds with a sat solver and then shrinks them into mousses. Every time Unimousse identifies such a mousse, it then applies a mousse replication technique on the mousse to identify additional seeds, and then it shrinks the seeds to additional mousses. Basically, the mousse replication works as follows. Assume that we found a seed S and then we shrunk it into a mousse, S mousse, like you can see on this picture. We now pick a clause C of the mousse, and then we attempt to find the seed N such that N contains the whole mousse except the clause C, and N is contained in the seed S. To find such N, we exploit the well-known concepts of backbone literals and backbone propagation. A backbone literal of a formula is a literal that is implied by the formula. The propagation of backbone literals can be used to simplify the formula and possibly to show that the formula is unsatisfiable. Crucially, observe that if we remove the clause C from the mousse, we get a satisfiable set of clauses, say T. Note that T implies the negation of the clause C, since adding C would make the formula unsatisfiable. Consequently, the negated literals of C are backbone literals of T. We can now propagate the backbone literals to simplify T. However, we already know that T is satisfiable. Instead, we use the propagation to show that some superset of T is unsatisfiable. Let me illustrate it on an example. Assume that the set S contains 5 clauses, not x1, not x2, x1 or x2, x1 or x3, and x2 or not x3. Moreover, let the mousse S mousse contain the clauses not x1, not x2, and x1 or x2. As the clause C, we choose x1 or x2. Consequently, the set T contains the clauses not x1 and not x2, and we also know that the literals not x1 and not x2 are backbone literals of T. Now we choose as the set N the clauses not x1, not x2, x1 or x3, and x2 or not x3. Note that N is a superset of T, which means that every backbone literal of T is also a backbone literal of N. Therefore, we can use the backbone literals of T to simplify N. In particular, if we propagate not x1 and not x2, we get this formula. And now we can easily see that N is unsatisfiable. So, we have seen on one particular example how to show that the particular set N is unsatisfiable just with propagating the backbone literals. However, the question is how to choose N. Recall that our objectives are to ensure that N is a seed. This means that N has to be both unsatisfiable, which we can prove with the backbone propagation, and also N has to be unexplored. Moreover, we would like to identify a small n, since small seeds are easy to be shrunk. For details on how we actually find such n, please refer to the paper. So we have sketched the idea how we can, based on a mousse and a similar closed C of the mousse, use the backbone propagation to identify a seed. In our mousse replication technique, we apply this procedure for every clause of the mousse, which means that we can identify several seeds. We shrink all the seeds into mousses, and subsequently we recursively apply the mousse replication on all the newly identified mousses. Consequently, mousse replication can possibly identify a large number of mousses. We have implemented Unimousse and experimentally compared it with 4 contemporary mousse enumeration algorithms: Marco, Mousse, Flint, and Remousse. As benchmarks, we use a collection of 300 formulas that were taken from the Mousse track of the SAT 2011 competition. Note that these benchmarks are standardly used in Mousse-related papers, and moreover they were used in the papers that presented our competitive algorithms. As a time limit, we used 1 hour per each benchmark. As the comparison criterion, we used the number of identified mousses within the time limit. Moreover, we have examined the manifestation of mousse replication in Unimousse. So let me first discuss the manifestation of mousse replication in Unimousse. Recall that mousse replication is the very first technique for identifying seeds in polynomial time without a SAT solver. Unfortunately, the technique is incomplete, which means that it sometimes fails to identify seeds even if there are some seeds. However, if the mousse replication works, then it can bring a significant improvement over the existing mousse enumeration algorithms. In this plot, on the x-axis, you can see individual benchmarks, and on the y-axis, you can see the percentage of seeds and consequently mousses that Unimousse identified via the mousse replication. You can see that in case of 50 benchmarks, mousse replication found no seed at all. However, in the case of the remaining benchmarks, mousse replication performed very well. In fact, in a majority of benchmarks, more than 99% of seeds and consequently mousses were identified by mousse replication. That is, these seeds were identified without the SAT solver. So that's for mousse replication. We now compare the number of mousses identified by Unimousse and by the other algorithms. On this slide, we provide 4 scatter plots. Each scatter plot compares Unimousse with one of the 4 competitors. Each point in the plot corresponds to a single benchmark and shows the number of mousses identified by the 2 algorithms. Algorithm that labels the x-axis determines the x-coordinate, and the algorithm on y-axis determines the y-coordinate. Unimousse always labels the x-axis. You can see that in comparison with Flint and Marco, Unimousse absolutely dominates. Besides few benchmarks, Unimousse always found more mousses than the 2 algorithms, and the difference was often several orders of magnitude. In the case of Mousse and Remousse, there are around 60 benchmarks where Unimousse found fewer mousses than the 2 algorithms. However, on the remaining majority of the benchmarks, Unimousse again conclusively dominates. So let me sum up. We have presented a novel mousse enumeration algorithm called Unimousse. The algorithm is based on the Csharing scheme, and it employs 2 novel techniques for finding seeds. One of the techniques is based on the SAT solver, and it explains the union of identified mousses to find small seeds. The other technique, called mousse replication, can identify seeds without the SAT solver, which means much faster than existing mousse enumeration algorithms. We have experimentally compared Unimousse to other contemporary mousse enumeration algorithms on a standard collection of benchmarks, and we have seen that Unimousse significantly dominates on a majority of benchmarks. Moreover, we have seen that Unimousse identifies a vast majority of seeds with mousse replication, which means in polynomial time without the SAT solver. Note that we found no correlation between benchmarks where Unimousse performs poorly and where mousse replication does not work. It is thus not the case that mousse replication would be the only important ingredient of the algorithm. All ingredients of Unimousse contribute to its efficiency. Finally, if you would like to try Unimousse, you can find it on GitHub. So that's it. Thank you for your attention, and if you have any question, just ask.